Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. So in the previous lecture we have proved this result, which on the face of it yet does not make much sense, because sense as in how is this going to actually help us in proving our subsequent synthesis results for H2 optimal control. We still do not have any clue about that, right. We have just shown that we have introduced this notion of what is an inner. We have shown that it is the equivalent of an orthogonal operator on Euclidean spaces, which is an orthogonal matrix essentially. And then we have seen that this particular case where you choose your u hat or this transfer function matrix u in a certain manner, then that will always turn out to be an inner. Okay. So to be precise, let us revisit the last result, which is very important indeed. Yeah. So this is the result that we had last seen. Okay. Let's suppose you have a plant ABCD, which is stabilizable and detectable, which is not really asking for much, because stabilizability and detectability is a bare essential we desire out of a plant, for which we want to design an internally stabilizing controller. So we want it to be stabilizable and detectable. We want this condition to be met. This D Hermitian acting on CD leads to this structure 0I. Yeah. And then we have this Hamiltonian, corresponding to which if we compose a Riccati equation, the Riccati operator, yeah, then we see that this Hamiltonian does belong to the Riccati domain of the Riccati operator, which means that there is a stabilizing solution x, in the sense that if you choose f is equal to minus B Hermitian x, yeah, then you see that A plus BF B C plus DF D is indeed an inner. In other words, it is norm preserving in the sense of this inner product that we have defined in the preceding lectures. Okay. So we have proved that indeed what is the sequence of steps? Given an ABCD, you find out, cook up this Hamiltonian, check that this mild condition written in red, boxed in red, is true. Then corresponding to this you find out the solution of the Riccati equation, let that solution be x, yeah. Then you define f, so maybe we can call it as defined. Okay. This is by definition, we are defining f to be minus B Hermitian x. Okay. With that being our feedback gain, the state feedback gain, right. If we cook up the new closed loop system A plus BF, B, C plus DF and D, then it will preserve the norm. Okay. But how on earth is this even important, and why is this going to be useful in our subsequent analysis? We still do not have any clue. So before we proceed further, let us just state another result. Okay. Not really a result, it's quite obvious really, it's just like some sort of a corollary, maybe not a corollary, I do not know, just a easy to see result. When I say easy to see, I mean that I am leaving the proof to you. So in easy to see result, it requires some bit of routine algebra, but I leave that to you as an exercise. Okay. It is an exercise, easy to see result for G1 in RH2 and G2 hat in RH2 perp, the orthogonal complement of this. You know, when two subspaces, one is the orthogonal complement of the other, that means everything that you pick up from RH2 in perp is going to be orthogonal with to any vector or any object in RH2. Yeah. When we say orthogonal, we mean if you take an inner product of a fellow in RH2 and a fellow in RH2 perp, then that inner product is going to lead to 0. Yeah. So, we have that the inner product G1, G2, yeah, in L2 hat. So, L2 hat is basically split up into RH2 and RH2 perp such that this is 0, and if Q hat belongs to RH2, then this is the interesting thing, the para-Hermitian conjugate of Q hat will belong to RH2 perp. So, this is actually the equivalent of the Paley-Wiener theorem, which we had again stated and shown you many lectures back. Yeah. The only difference being that there we were not talking about systems, we were talking about signals, here we are talking about operators now. Okay. So, this is the equivalent revisit, I mean this is not exactly Paley-Wiener theorem. So, this is basically going to shadow the Paley-Wiener theorem that we had talked about earlier, similar in flavor to the Paley-Wiener theorem. Okay. So, we will just just as an observation, actually this is like an observation, you can just check out, you can try on your own and you can check out that this is indeed going to be the case. Okay. All right. Now we are going to really prove some important results. So, maybe I call them theorems. Let us call this theorem 1. It is going to be a longish statement, but the payoff at the end is big. So, bear with me. Suppose you have G hat given by the packed matrix notation A is very typical B1, B2, C1, C2, 0, D12, D21, 0. So, the well posedness revisit, again we had discussed this earlier, the well posedness of this sort of a system with a D matrix given like so is basically guaranteed. Okay. So, suppose this is our plant that we wish to internally stabilize and also at the same time get an optimal controller for this, an in an H2 sense. Okay. And firstly, A, B, I, C, I is stabilizable and detectable for I is equal to 1, 2. In other words, A, B1, C1 is stabilizable and detectable, and A, B2, C2 is also stabilizable and detectable. Okay. Second, the first proposition, second, D12 Hermitian C1 D12 is equal to 0 I. Things are exactly in place where we want them to be. This is exactly a part of the clause that we had in the preceding day's result, right, that this D12 Hermitian C must be 0 and D12 Hermitian D12 is equal to I. So, things seem to be exactly in place for us to be able to show that something is an inner. What is that thing? Well, you might be already able to foresee what we are trying to do here, but in case it is not very clear, we will do it momentarily in a few moments from now. Okay. So, this is the clause. Furthermore, if K hat is an internally stabilizing controller for G hat, then the closed loop performance satisfies, observe very carefully what we are doing. There will be a lot of terms that we will define. Do not get waylaid and lost in the midst of all that. Yeah, we are introducing GC for instance here, which we have not yet defined, but we will do so shortly. Now we are defining GTMP, again something that looks like too much complication, right? Where GC hat is equal to A plus B2F C1 plus D1 to F I 0 GTMP hat is equal to A B1 B2 0 I D210 minus F C2. What is F? F is equal to minus B2 Hermitian X. What is X? X is equal to the solution of the Riccati equation obtained from the elements of HC. And what is HC? So, there is a sequence of steps, you see. That is why I said it is a big statement, you have to concentrate a bit. Okay. So, tracing our steps back, what do we see? You have been given a plant. So, to summarize things, you have been given a plant specified by A, B1, B2, C1, C2, D1 to D21, like so. The bare minimum we ask from this plant is that A, B1, C1 is stabilizable and detectable, A, B2, C2 is stabilizable and detectable, and the fact that D1 to Hermitian C, D1 to is equal to 0I. Yeah, this is given. Unless this is given, then we cannot do much. Okay, so this is bare minimum which is given to us. Now, we are trying to formulate a condition when we will be able to get an internally stabilizing controller for such a plant in the form of this K hat. Okay, and furthermore, this K hat will also meet certain performance metric in the sense that the norm that we are trying to minimize, that is the starred product. So, what is this S bar? Remember again 2 or 3 lectures back we discussed what is this S bar. It is basically the starred product, that means you have the usual connection block, no, the W coming in and the Z coming out, those are the signal, exogenous signal and the output signal Z, and then the Y is fed back through the controller and that spits out U, which is fed back to the plant. So, it is a typical plant controller combination, and the star product is what we had called it. Again, revisit when we defined this as a star product 2-3 lectures back. So, that is the star product. So, the norm of this star product, which is nothing but the transfer function from your W to Z, and remember the Z were something like the error variables in tracking. So, we want to minimize this norm. So, we want to choose a controller which minimizes this norm. So, what we have now is, if this expression is indeed true, this expression that is the one I am marking now in this here, if this expression is indeed true, then it says that the key to minimizing this norm of the star product of G hat K is in focusing our attention on this term, because this term is free of K. This is free from K hat. So, if you want to minimize this, you had better turn your attention towards minimizing this. Yeah, this is a good indication, right? It is very helpful actually, the observation that this is indeed the case. Okay. So, that is why all this GTMP and all these auxiliary things that we have defined here, they are going to be very important. Okay. So, this is an important result. So, given this ABCD structure, we get this Hamiltonian, get its corresponding Riccati equation, solve that Riccati equation, get its x, yeah, then take minus B2 Hermitian x, define that as the f, okay, and then we say that get this GC as A plus B to F I C1 plus D1 to F 0. So, this is the A matrix, B matrix, C matrix and D matrix, okay, and this is what we define as the GC, okay, and we say that this is going to lead to our minimization, Okay. So, let us see how this whole thing is meant to work out. Yeah. So, how do we expect this such a system to work out? That is the main question. So, we will try to prove this result now. Okay. So, what will be our different steps for proving this? Now, suppose we take condition 1. So, from condition 1 what can we say? We may infer that HC belongs to domain of Riccati, right? It is a no brainer again, right. What is condition 1? That A B1 C1 and A B2 C2 are stabilizable and detectable, therefore, it belongs to the domain of this Riccati operator that we have cooked up, no? Yeah, this is not really that difficult to see, right. You can take this up as an exercise if you are not convinced that it is indeed the case. Yeah. What do you have to check in order to do this? Go back to the lecture, the results we derived around 2 lectures back, and see that if this is indeed the case, then we can always claim that it satisfies the conditions for HC to belong to the domain of the Riccati operator. Okay. Further, X and F will be well defined, yeah, and A plus B2F is Hurwitz, because it is a stabilizing controller, so it must be Hurwitz. Yeah. So, if it is Hurwitz, therefore, GC hat must belong to RH2, because what is GC hat? Notice what is GC hat. If A plus B2F is Hurwitz, then GC hat is stable, right. This transfer function is going to be stable. So, therefore, it belongs to RH2. It is really not that difficult to see. Now, S bar, the star product of G hat, K hat, yeah, what is this known as? Let us write down the state space. Can be represented in state space domain as x dot is equal to Ax plus B1W plus B2U, Z is equal to C1x plus D12U. Remember what is the representation of G here? Yeah. So, A, B1, C1. So, this is X, W. You can just, for shorthand notation, you can check this is X, W and this is X, W and U, and this is X. So, if you read through the horizontal lines, the first block is X, then is W, then it is U. If you read through vertically along the along the rows, and then this is X, this is the output Z, and this corresponds to the output. So, this corresponds to the output Y, right. Okay. So, knowing that to be the case, we can write Y is equal to C2x plus D21W. Please note that it is not fitting in the same window for me, but you can always check when you are writing this down. Flip through the pages of your exercise book and you will find that the representation that I have made of G hat is indeed correct, but now I have to combine this with the expression for K hat. So, the states of the controller are represented by xk. So, xk hat dot is equal to ak xk plus bk y, because y is fed into the controller. It is the output that is used for feedback, right. And the output of the controller is the control signal which is fed to the plant in turn. So, this is ck xk plus dk y. Okay. So, this is our entire representation. Okay. Now, if we focus on GTMP, yeah, then what do we get? Notice the representation of GTMP here. Yeah, you notice this. Let me draw your attention with a red mark or really a yellow mark here. This line. What does this say? Yeah. Let us call this variable for this G. Let us call this variable V. All right. What is this V after all? We get that V is equal to nothing but minus fx plus u. Remember this GTMP is some auxiliary kind of a system that we had constructed artificially in order to get a handle over this entire norm expression for this norm, right. So, we are just interested in this particular row, okay. Let us call this V. So, this is minus fx. So, this is some system that is cooked up using the same states of the system as in G, those same states, because the A matrix is the same. Only thing is that the C matrix changes, right. So, instead of cooking up the signal Z using C and I, yeah, we are now using minus F and I. There you had C1 and D12. So, instead of that everything else remains same in G hat temp TMP except for the signal V, which is slightly different, yeah, is the only difference from G. So, basically this replaces this, yeah, that is the only difference. Okay. So, bear with me a little. What are we therefore saying? Then the closed loop matrix ACL for GTMP is same as that of G hat. What I mean by that is, if you put GTMP now in place of G in the star product, the closed loop matrix ACL that you will be getting is the same. Yeah. Okay. Hence, what we are now going to claim is that any K, any controller that stabilizes G must also stabilize GTMP and vice versa. In other words, the question about obtaining a stabilizing controller for G and that for GTMP are equivalent questions. Hence, any K hat that stabilizes G hat must also stabilize G hat TMP. Furthermore, we have that G hat is proper is equivalent to saying G hat TMP is proper. Look at the structures of the D matrices in these two, yeah, and the C matrices, and you will immediately be able to infer that whenever GTMP is proper, so is G hat, and whenever G hat is proper, so is G hat TMP. Yeah. So, all these equivalences finally lead us to what? let u is equal to v plus fx. Okay. Notice what did we originally have here? We had this controller ckx plus dky, but we are saying that now look, let u be equal to v plus fx be used in let us say these two blocks taken together star. So, I say okay. In other words, we are saying that this is all we are going to use. Okay. From this V that we have gotten from this GTMP, we are going to use it. So, let us see what the consequence of this is. This leads to x dot is equal to a plus b2f x plus b1w plus b2v, and z is equal to c1 plus d12f times x plus d12v. In other words, if we now look at the transfer function, then z hat s is equal to gc hat s times b1 on w hat s, yeah, plus u hat s times v hat s, where u hat s is a plus b2f, c plus d12f, b2 d12. Fantastic. What do we have now? Notice this GC that we have defined in the statement of the theorem here, yeah, this is exactly what GC is, right? And now this GC is exactly what is also capturing our relation between W and Z. Notice that there is no W related term here in this Z equation, no. So, therefore, the D corresponding to W is 0, right. So, if I write the packed matrix notation for the transfer function between Z and W, what will it contain? It will contain this as the A matrix, this B1 as the B matrix, this C1 plus D12F as the C matrix, and 0 as the D matrix. But that is exactly nothing but GC, the way we have defined this GC hat in our statement of the theorem. Look, this is exactly what GC is. So, indeed the transfer function between these variables, that is W and Z hat, is actually this GC times B1. Why this B1? Because of course, you can just treat W tilde as sort of B1W, and then you will immediately see that this is the case, right. Yeah, because GC had I in its B entry, see. Notice that we had a I here, right. So, that is why that B has to be post multiplied here, right. Okay. And furthermore, by the same token, you can also check that this U hat, this captures the transfer function between V hat and Z. So, now V hat, that for that the D matrix is sitting here, the B matrix is sitting here, the A matrix is of course the same, and the C matrix is also the same, right. So, this is clear to us. Moreover, V hat is equal to V hat S is equal to the star product of G hat TMP and the controller K hat acting on W hat S, right. Why is this the case? Notice that when we defined it in this manner, that is exactly what we did, no. we said that look, we are going to construct an artificial system GTMP by replacing this Z defined in original G with a new variable V defined in this manner, where the C1 got replaced with minus f and this D12 got replaced with identity, right. So, this was an artificially constructed system, this G hat TMP that we have constructed, it is an artificially constructed system, right. So, now if you are looking at this V hat, we have to look at, we have to just supplant this equation for this equation here, yeah, that is going to be our G temp, everything else remains the same, only that this equation replaces this. So, this equation goes in place of this and we get our GTMP, right. So, when we try to find out the transfer function between the V, which stands as a proxy for Z, yeah, which is this V here, when we replace this V and we try to find out the transfer function between this W and this V, that is all we need to do. That is nothing but the star product of this GTMP now instead of the original G, yeah, that gives us a transfer function. But this means what? Now notice that this S bar, G hat, K hat, we have already written this is equal to what? Okay, let me write it down in 2 steps then. So, from this step here we can write Z hat S is equal to G hat C S B1 W hat S plus U hat S times, now we are going to replace this with S bar G hat TMP K hat acting on W hat S. But this means that the overall star product which gives me the transfer function between W hat and Z hat, which is the star product between G hat and K hat, is nothing but this GC hat B1 plus U hat acting on the star product of G hat TMP comma K. This is beautiful. Now we have one term which is completely freed up from K and only one term which depends on K. This is now going to lead us to our desired result that we are trying to prove. So, there are 2 things that we will now, okay, before that let us write that down then we take inner product on both sides with itself, or rather we take the norm on either side, G hat K hat squared is equal to, this is very standard, you can check in any inner product space, plus the norm of U hat, the star product of G hat TMP K hat norm plus twice the real part of the inner product of U hat S bar, this is the star product of G hat TMP K hat with GC hat B1. Okay. Now, we make 2 important observations here. One, observe that U hat is inner. We proved this already, right, that the U hat that we have obtained here, and that is why it was so important. Notice that this U hat we proved in the earlier part previously, that this U hat is indeed inner. So, if this U hat is inner, okay, we will come to what that will lead to. Already you can see if the U hat is inner, then this norm will remain invariant under the action of U hat. So, the norm of this is the same as the norm of the star product of G temp and K hat alone. Yeah, you can get rid of this U hat, it matters not in terms of the norm, okay. But we will write that all finally in a nice manner. The next thing that I am going to show you is, again, those who are familiar with inner product spaces and adjoint operators, they will see immediately the connection. Notice that this para-Hermitian conjugate acts exactly like the adjoint operator on inner product spaces. So, in other words, the second observation is that U hat S bar G hat TMP K hat comma GC hat B1 is the same as S bar G hat TMP K hat comma. So, this now stands in as the adjoint operator in inner product spaces, which is the para-Hermitian conjugate of this EU, GC hat B1. All right. But what do we know about this? So, based on these two observations, let me put these observations again in a box here. This implies that the star product of G hat K hat squared is equal to norm of GC hat B1 squared plus, notice now I am going to get rid of this U hat, yeah, because it is an inner, therefore, it does not matter in the evaluation of the norm. G TMP hat K hat, this norm square. Now, this is going to be interesting. What can I say about this fellow here? This fellow belongs to RH2, okay. But this fellow, because of its association with this U hat inner, yeah, this belongs to RH2 perp, yeah. If you do not believe me, you can try checking it out yourself, that when you have this U hat and you take its inner, you take its para-Hermitian conjugate, yeah, that will always belong to RH2 perp, okay. So, this means that this inner product is nothing but 0, which means that of course, its real part is also going to vanish. So, all that we are left with is now just this, which is exactly what our result has claimed. What does this mean? The great thing about this is that now if you want to minimize this norm, it turns out that this is the minimum penalty that we must pay, okay. We cannot minimize this norm beyond a certain point such as this, okay. Yeah. So, the only thing that we can hope for is if we can sort of minimize the second term in this equation, that is this star product of G temp, G hat temp with K, if we can minimize this one, then we will be able to sort of get a handle over this problem, right. So, this is a great result because now we know exactly what to focus on. Hereafter, instead of focusing on minimizing this original problem, we can turn our attention to focusing on this term here and looking at this particular transfer function G hat TMP and seeing that what sort of, and investigating as to what sort of K hat will minimize this norm, because that will exactly be the minimizer for the original plant. In this manner, we have just transformed the original problem of looking at the original G hat into looking at the artificially created system G hat temp. It reminds you of something else, does it not? Yeah. Remember when we are looking at internally stabilizing controller much earlier, we also constructed some artificial system, right. So, this is again a very usual trick. We go from an original system to a system that is easier to handle, that is simpler to deal with, that is more tractable. So, in this case it is this G hat temp that we shall now be concerned with hereafter. Now, we set for ourselves this apparently ambitious goal of minimizing the star product of g hat temp comma k hat, yeah, for a suitable internally stabilizing k hat. Okay. So, one observation, we can state it as a corollary for a simple state feedback controller, which is when we assume that all our states are available at the output right away. We can observe all the states directly, that is the C matrix is the identity. We already have a minimizer, yeah. What is that? Notice here, what did we choose? Yeah, what did we choose here, and why is this going to be a minimizer? Yeah, because if we are choosing our state feedback, then we only have a static controller, right. So, the controller does not have any other dynamics. So, let us go back to this controller structure that we have in the proof. Yeah, right. So, if you have a state feedback here, you will notice that this everything that is there, this C1 is already an identity, no? Yeah. I mean sorry, the y is already an identity that is being fed. So, C2 is already identity here, right. So, if we want go for the state feedback, then C2 is already identity for us. So, that means we can already feedback all the states directly through whatever state feedback we design, right. So, in that case, if you plug in here, where is it? Yeah, if you plug in here in this expression, in this minimum expression, I can leave that to you as an exercise. I believe that you can see that this is already going to minimize this for the state feedback case. Yeah, you can check that. What happens to the GTMP is what will tell you the answer to this question. Look at GTMP here. Yeah, just add suitably whatever this happens to this GTMP and you have your answer. Okay. So, anyway, this is just a curious observation. We will not dwell much longer on this special case of state feedback alone, yeah, because we are dealing with a general dynamic controller here, in which case we cannot assume, I mean that is only relevant in the case when we cannot assume that the states are all available readily for us to be used as a feedback, which is obviously very restrictive assumption in general, right. So, now we go on to the next result, and probably this is the final result that we will have time for in this particular lecture. So, let us, what did I call the previous result? Result 1, is it? Oh, theorem 1. So, let us prove another theorem, let us call it theorem 2. We will prove theorem 2 now. Suppose G hat has a realization A, B, C, D, and K hat has a realization AK, BK, CK, DK. Okay. Suppose these are the two realizations and gamma is a real number that is greater than 0. Okay. Then the following are equivalent. What? What is equivalent to what? K internally stabilizes G and the star product's norm between G hat and K hat is equal to gamma, and 2 that K transpose internally stabilizes G transpose and the star product of G hat transpose K hat transpose. So, these are simple transposes, by the way, yeah, is equal to gamma with, so we will define shortly what is this simple transpose. G hat transpose is equal to A Hermitian, C Hermitian, B Hermitian, D Hermitian, and K transpose, K hat transpose is equal to A K Hermitian, B K Hermitian, C K Hermitian, oh sorry, yeah, D K Hermitian. I think I have just got to flip it. Yeah, C K Hermitian, B K Hermitian. So, these are simple transposes, not conjugations. Okay. So, these are equivalent, you see. In other words, what it says is that whether you take the norm of original G K or you take the norm of the transpose, they are going to be one and the same. Yeah, and so it is basically like a duality kind of a thing. Yeah, these are just transposes. Okay. So, I will just say that, yeah, these are just transposes. Okay. Apart from this, we will also now discuss some other result. We will not state this in the form of a theorem. We will state this in the, we will not state this in the form of a theorem. We write down some observations. These will be handy in subsequent proofs. Suppose E hat is defined in the following manner: A minus L B2 minus F C2 0 0 I. Another artificial system that I am cooking up. Okay, do bear with me for a while. Okay, and K hat or K2 hat is defined in the following manner: A plus B2F plus LC2 minus L and F 0. So, this is kind of again routine algebra. You can check that the norm preserving, I mean the norms of these two are unchanged under this sort of a transposition or Hermitian operation. Now, you might think, okay, where am I getting all this E hat and K hat from? These will be relevant when we try and prove the big result. So, just do bear with me for a while I again define another artificial. Already we have defined an artificial system G hat temp, right, and we have seen that obtaining the optimal controller is for the original plant G hat is tantamount to obtaining the optimal controller for G hat temp. Okay. But now in order to massage this G hat temp in a tractable form, it will turn out that we will need this E hat. So I am just giving it to you now as a result that this E hat will be useful. So I am stating it in a reverse manner, but you will see things fall back nicely in place when we are through with proving all of these results. So I am just making a few observations here, and we will stop after I have made this observation and convinced you about the veracity of the same. Okay, that is where we will stop for today's lecture. So let us look at this E hat here and this K2 hat here. Okay. Now what does this state space realization of this E hat and this K2 hat together entail? We can write x dot is equal to Ax minus Lw plus B2u, z is equal to minus Fx plus u, y is equal to C2x plus w. Of course, the controllers xk dot is equal to A plus B2f plus LC2 times xk minus Ly, and u is given by Fxk. Okay. So we have written down basically the overall equations as they would appear if you had to take a star product. This is all part of the star product, the usual configuration. So next time when I write this sort of equation, you will immediately know we have put the plant and controller in the 2 by 2 block form, like so. Okay. So now what does this entail? If we write this in the packed matrix notation, this is tantamount to A B2f, because u remember is just Fxk, right, A B2f minus Lc2 and A plus B2f plus Lc2. It is just routine algebra, okay, nothing fancy at all. Yeah, this y I can substitute as C2x plus w here. So I write this as C2x plus w here, and this u I write as Fx here. That is all that I have done, and that is all that you need to do in order to write this interconnection. And then there is this minus L and minus F and a 0 here. Okay. This is the packed matrix notation for this entire star product configuration. Okay. So this is basically the star product of E hat and K2 hat, okay, in packed matrix notation. Now let T is equal to I minus I 0 I, T inverse is equal to I 0 I. Okay. Check that T A B2f, I am applying this transformation on the star product, yeah, it is of size equal to the, so this I is of size equal to the controller and plant, they are of the same size we have taken, right, for the, this is A plus B2f plus LC2 times T inverse, and you can check that this turns out to be A plus LC2 0. So I have done this operation earlier, so I remembered this. This in fact was very useful in proving our separation principle, if you recall, right, the observer and controller separation principle. So this is our A bar closed loop. Similarly, consider minus L, that is our B matrix. So consider Bt is equal to I minus I 0 I, that is equal to, oh I am sorry, that is actually the, yeah, sorry, completely flipped. So, it is going to be TB, right? Yeah, it is going to be TB. Yeah, TB. That is going to be equal to what is T? I minus I0 I. Yeah, so that is going to be equal to 0 minus L, okay, and C T inverse, that is going to be equal to minus F and F I 0 I minus F 0. So, in other words, we have a ABC matrix in the with a change of basis which is given by A plus LC2 0 minus LC2 A plus BF, sorry, A plus BF2, okay, that is A bar. The B bar is given by 0 minus L, and the C bar is given by minus F 0, okay, sorry, it is not a tall matrix, my bad, minus F 0. Now, what does this tell us? If you now try and check, it's a matter of routine check, right? If you try to check for this sort of a structure, it's a block triangular structure that you have here, right? So, you see that no matter what inputs you apply, none of these first n states are going to be influenced by it, yeah, and no matter what happens to the last n states, they are not going to be reflected in the output, yeah. So, those states are not observable. In other words, the only states that reflect at the output are the uncontrollable states. So, there is no way that any influence of the input is visible at the output. In other words, this has the makings exactly of what we are looking for, right, what we have discussed so long, which is that the ABC matrix, you see, it devolves, it degenerates, yeah, because there is no D matrix here, because there is no D matrix here. What can we say about this? That if you take the star product of this E with K2, if you take the transfer function between this, between a signal that is injected at the input of this EK block, like E is the plant and K2 is the controller, then can we not say that the star product of E and K2 hat is actually equal to 0, yeah, seen as a transfer function it is 0. In other words, the norm of this S, the star product E hat K2 is obviously then by default going to be 0, yeah. This is going to be immensely useful to us, okay. In what follows, when we will try to get a handle over this GTMP, that we will try to now next minimize using our controller, yeah, which is going to be the final piece in the puzzle, we will see that this observation, that this artificially cooked up system E hat, its star product with K2, the fact that it leads to a 0 transfer function is immensely important, okay. So, please note down this observation. This is sort of a minor result, it is sort of an intermediate step, but once you recall this, you will see that immediately the proof of the main result that we are shooting for will follow, okay. So, we will hopefully be able to take a look at that in the next lecture. The details of the proof and the synthesis problem will complete. Okay. So, till then take very good care. See you in the next lecture. Thank you.